Hey everyone, for the last part of the Coyotes versus Wolves lecture series, we're going to be doing a little bit of Python code to be writing up the plots, but also just the functions that we've talked about before, both just the Bayes formula and also just the optimal decision boundaries. We'll be learning about how to plot and also how to compute in Python right now. This environment that you're seeing right now is the Google Collaboratory link that is on the website for the course. So feel free to just give it a click and then you'll hop into the same page that I'm in right now. Overall, Google Colab is a Python notebook environment. And by notebook, I mean just it's a dynamic, by dynamic, I mean that you can run code on the fly. You don't need to run the whole program. Dynamic Python environment such that you can write little snippets of code, like you can see in the little blocks, and they will run individually. And so you can go ahead and change the blocks, the individual code that's running in the blocks, and then just mix and match. And so it makes it really easy to do exploratory work, but also just when you want to just test something very quickly with code, how to just do that in a notebook very quickly. It's very easy. And so to start off with, this is kind of going to be learning via fire hose. There's going to be a lot thrown at you right now, and not all of it's going to stick, and that's okay. But overall, I'm going to be showing you how to do both sets of problems, both the one that we worked off the table with the exact counts, and then also the one with the normal distribution. How do you actually calculate the optimal decision boundary? And then how do you plot the normal distribution? The first block of code that we'll see, I'm just going to go ahead and dive in. The first block of code that we'll see is the import libraries. So NumPy is a numerical Python library that just helps us do math and math very easily. So what a library basically means is that some group of individuals wrote a piece of software that has an API, things that you can access via programs. And so, for example, a NumPy, the library, has a function within it that I can call that gives me a normal distribution. So I can basically pick from the normal distribution, and that's included in NumPy. Matplotlib provides me the graphics for which I can plot data. And so instead of having to just generate an image or a picture and then draw the actual axes, label the axes, put in the legend, Matplotlib provides me the software that I can just interact with my program, my Python program, and just on the fly generate a plot. And so those are the two things that we're going to be using right off the bat. And without further ado, we'll go ahead and just jump in right with the first problem. And so the first thing that we need to define is the total population. We were working in the Arizona Sonora Desert Museum. We were working with 100 animals before, and we can totally continue doing 100 animals. So I'm just going to be declaring a variable equal to 100. And so how you do that in Python, you can see on the left, we have that total pop, that's a variable, and then we've got the numerical value, which is 100. In some languages, you might need to say that this is an integer because it is a number that doesn't have a decimal. However, in Python, it will automatically understand what kind of number it is. A different kind of number you can see is the probability of wolf. And so probabilities are between 0 and 1, and we need to represent that as a float or a decimal value. And so it's called a float in Python. And so that means that we have precision past the decimal place. And so 0.2, that's some precision. And then you can see the first example of a mathematical operation where we have the probability of coyote is equal to 1 minus the probability of a wolf. And this will evaluate to 0.8 in our specific case, but it doesn't necessarily have to. We can just mix and match the values. And so the overall first block of code, what we're looking at is just trying to enumerate some of the facts that we know about the problem. The Coyotes versus Wolves in the table format. We know that there's a probability for wolves and coyotes population, and we know that the probability of tall given a wolf and probability of tall given a coyote is different amongst the populations. And so from the calculations that we did in 3 or 4 lecture videos ago, we know that the probability of a tall given a wolf is 80%, and similarly, probability of tall given a coyote is about 20%. And so you have a lot more tall wolves than you do tall coyotes, even though if the probabilities were equal, they would have the same number of population size. But that in our first case, we will not allow that, and we can see how that changes. Before I actually run this code, I'm going to continue just evaluating line by line, and then from there we'll run it and then look at what the output is. Again, we're just enumerating some facts. How do we get the 4 elements in our table? The tall wolf, short wolf, tall coyote, short coyote. We just take the total population times the probability of our animal type times the probability of tall given the animal type, or probability of short given the animal type. And so you can see that we've got count of tall wolves is equal to total population times the wolf probability times probability of tall given wolf. Similarly, we've got the coyotes. And with these 2 counts, we can go ahead and do the opposite side of it, where we're doing the count of the short wolf, where we have total population times probability of wolf minus whatever we calculated before, count of tall wolf. Similarly, for short coyote, do the same thing. And here we're going to actually try to output our results. And so this is a function in Python. It's called print. I'm writing F because I'm basically going to be putting in values within our print. Again, this is learning via fire hose. You're not necessarily supposed to have everything stick right now, but this is just an example of how you output in a print statement. And so we've got a string here where the number of tall wolves is equal to the value that we had just calculated before. And this is an integer. And so I just do this to make it look clean on the output, but we didn't need to do that in general. And so I'm going to print out the number of tall wolves, number of tall coyotes, short wolves, short coyotes, and then overall, I'm going to sum it up and do the total population count just to make sure that it's the same as the 100 that we see before. And so I'm going to go ahead and run it, and we can, you're going to get this warning just because it just wants to make sure that you're running code that you know. So the number of tall wolves, 16, number of tall coyotes is equal to 16, number of short wolves equal to 4, number of short coyotes is equal to 64. Total population is 100 again. So we're good to go. That just checks out. Then we can apply the Bayes theorem to actually solve our formula. This is the first example of a function that we'll be seeing in Python, where we have to declare a function with this def keyword. That means a definition. And then this is the function name, Bayes theorem, where we have a probability of an animal type, probability of height given the animal type, and then probability of height. This is the same exact formula that we saw before, except we're now just putting it in code. And we have to tell the function what we want it to return. We want it to return the probability of height given the animal type times the probability of the animal type divided by the overall probability of height. And so we can mix and match these values if we wanted to get different answers, but for our specific purpose, we wanted to see the probability of a tall animal being more likely a wolf or coyote. And so then we can directly enumerate it. The probability of a tall animal being a wolf is equal to the Bayes theorem of exactly the probability of a wolf, which is the probability of the animal type, probability of tall given wolf, which is the second argument in our function. And then we also have the probability of height, which is equal to the count of the tall wolves plus the count of the tall coyotes divided by the total population. And so since it's the same, it will evaluate, when we were doing it before, it will evaluate or it will cancel out in our evaluation. But in order to get the actual probability, we may want to include it. And so we're just doing this for example's sake. Similarly, we have the same thing with the tall animal being a coyote, where we're plugging in the Bayes theorem and probability of coyote, probability of tall given a coyote, and then the same exact count as we had before for the probability of height. And so I'll run it just again, just to give you, the output. But we saw before the total population of 100, which was our logic check. And then we can see the probability of a tall animal being a wolf is equal to 0.5, basically. And you see that there's all of these other numbers after the 0.5. This is actually a deeper problem in how you compute numbers in computers, how you calculate numbers in computers. Computers are by definition or just by invention imperfect machines, but they do a great job at approximating. And so these are just general approximations that come from some of the errors that have accumulated in our operations. And so you don't need to worry about this too much. The probability of a tall animal being a wolf is about half. And so let's just plug and play. Now we've already done the code. And the nice thing about code is that now we've already enumerated what we need to run. We can go ahead and just change these couple of variables at the top. So if we wanted to evaluate a 1,000 person population or 1,000 animal population, we can go ahead and do it. right away, we'll get the same answer where you can see that the number of tall wolves, short coyotes, or sorry, tall coyotes, short wolves, and short coyotes have all changed. However, our actual probability calculations didn't. And you can see from the evaluation that we did in the homework, but also in the previous lectures, that we didn't actually need the population count or how many were there. We just need the probabilities. And so this checks out, we're all good. Let's change some other variables. Let's say that the probability is about half for the encounterance of a wolf or a coyote. Again, you can see how this has changed. We can see that the tall wolves is 400, tall coyotes is 100, short wolves is 100, short coyotes is 400. And so 500 populations each evaluates to a total population of 1,000. That makes sense. And then you can see that the probability of being a tall wolf or the animal being a wolf is actually 80%. And so now you can see that if we make the populations same size and we say that the probability of a tall wolf is greater than the short or tall coyote, that's kind of maybe obvious why we should get more likely the tall animal being a wolf. However, if we change the overall probability balance, it's not so obvious what would happen. And so this code gives us a way to evaluate that. And so go ahead and hopping into the next example, which is about our normal distribution. We're doing kind of the same thing as before, where we have a total population, we have a wolf probability and a coyote probability. And then the two values that we talked about before were mu and sigma. And so we have a wolf mu, which means that the average height or the mean height of a wolf, and then the coyote mu, which is the mean height or average height of a coyote. And we had a sigma, which is their standard deviation, and we are assuming it's the same for all the problems, so we don't need to worry about that. How do we actually do this, though? How do we actually evaluate this via code? So we did the evaluation in pure analytical form, where we were just looking at the variables, we were looking at what the normal distribution form is, and then just canceling out as much as we could. In order to do this in Python and how to evaluate this in practical terms, we can go ahead and leverage some of the libraries that we've imported, specifically the NumPy library, where we're going to go ahead and plug in the two values for the normal distribution that we have enumerated before, where we have the coyote mu and we have the sigma, and then we also just want to enumerate how many samples we want. So by samples, I mean that how many coyotes or wolves there are. And so we have a total population, we have the probability of a coyote or a wolf. And so we can go ahead and just multiply those and then just take the integer value. So we get a whole number because we can't have half a coyote or half a wolf. And so from there, we can basically use NumPy to say, hey, give me a normal distribution that has 500 values from this mu and sigma. And so what this will return, the coyotes and wolves over here, is something called an array. And this is just a list of numbers that represents the height of our coyotes and wolves. And so the coyotes and wolves, basically right here, if I go ahead and print coyotes, print wolves. Oh, I've got to run the import library. You can see that it just gives us a bunch of numbers and none of it really makes sense. But what this represents is our population of 500 coyotes and 500 wolves in the respective heights. And so you can see that, coyote number one has a height of 1.6, 1.62, 1.83. And so this is pulling samples from the distribution that we have enumerated. And so I'm going to go ahead and comment that out, run it again so that it looks nice and pretty again. And then we're going to go ahead and just do a logic check. The number of wolves and the average height of our wolves is, we're going to go ahead and do something called a length calculation. So we're going to take this array, see how many values are in it, which basically means how big the population is. And then we're going to go ahead and call an API from the NumPy library, which is the mean. And so we can do NP, which is the NumPy library dot mean, and we're going to pass in the array to get the average height of it. And so we should be expecting our average height to be around the mu, because this is like we're only pulling 500 samples and not like 100,000 samples. It might be off by a little bit, but we don't need to worry too much. Again, this is kind of goes through the same vein of computers being imperfect and us just doing approximations about the data that we have. And so I'm going to go ahead and run it again. The number of wolves is equal to 500. The average height is 2.29, which is right next to 2.3. And then same thing with coyotes, 500, 1.8. Perfect. All right. We got that. That evaluates to a logic check. We're all good with that. Now we can go ahead and plot for our normal distribution. So now we have 500 values from our normal distribution, and we would like to calculate what the optimal decision boundary is. We would like to just plot it in Python so that if we have any arbitrary size of values, we can go ahead with it and plot it. So we'll go ahead and do that with a histogram. And so Matplotlib, that's what we're using for the plotting. We are using the Python plot library specifically. So it's a huge, Matplotlib is huge. There's a lot of different things you can do with it. We're just specifically going to be looking at the Python plots with the histogram. And so just like before, we can use our array that we have generated. In the second value is the number of bins. And so in a histogram, we're going to chunk it out into individual boxes or bins, of which we want to say how many animals or how many wolves or coyotes are between like 1.2 and 1.3, and that would be a bin. And we would want the height of the bin is equal to, potentially the number of animals that are in that height range. And so we're going to go ahead and do 30 bins. We can change this. This just changes the look of the plot, not too important. And then we're going to head and do a probability density function. And so it's important to note that the probability density function is different than the actual probabilities of a certain height. So probability density functions, the only thing that it guarantees is that the sum of the area under the curve is equal to 1, is that the overall probability of something happening in this space is equal to 1. However, if you look in the x-axis, I know I'm jumping ahead, even on the thumbnail, you can see that of the last lecture that this is, between 0 and 2.5. 2.5 is not a probability value. And this is just something to notice and recognize that you can scale it to represent the probability on the y-axis, but that's not the plot that we care about. We want to plot a PDF, which is a probability density function, such that it abides that the overall probability under the curve is equal to 1. And so this is just something to note if you haven't worked with this before, but don't worry about it. Again, this is drinking by a fire hose. Not everything's going to stick, but we'll get more familiar with it as the course goes on. So we are going to go ahead and just generate the histogram, and that just generates the orange and the blue bars that you can see in the bottom. And then what we want to do is we want to plot the normal distribution over the plot. And so we have the mu and the sigma, and we have the equation from before. And so all we're doing in these two lines is actually just plugging in our x values that we want to plot, which is the start values of the VINs. So basically what x values we want to evaluate the normal distribution at, and then we have our normal distribution function. And so this is basically plotting our red and the blue line right here based off of the mu and sigma that we gave to the wolf and the coyote populations. From there, I'm going ahead and just kind of cheat because we're not going to do analytical calculations again. We already knew with the probabilities being equal that the classifying line or the optimal decision boundary is equal to the wolf mu plus the coyote mu divided by 2. And so I'm just going to go ahead and plot that. This is the green line that you see here. And then I'm going to say that an animal should be classified as a wolf. It's greater than the classifying line. You can kind of see the output already, but this just gives us a nice visualization of what's happening in the problem. And via our analytical solution, we know that this is the optimal decision boundary because of two things. One, that from our calculations, it falls through, but two, visually, looking at the plot, you can see that the intersection of the green and blue happens at the red and blue happens at the green. And so that just kind of just conceptually makes sense, because if you have a likelihood or, the probability densities of something being one thing or another is equal at a specific height, it's almost like it's 50-50. You don't know whether it's going to be a wolf or a coyote. And that's what the optimal decision boundary tells us, is that at this height, we can only make a guess, really. We have no sorts of greater probability than 50%. And so this is just the first example. The second example is the exact same code, except the fact that we have changed the wolf and the coyote probabilities, so that the wolf probability is like 0.3 and the coyote probability is 1 minus the wolf probability. And we're doing the same calculations, except that our classifying line is different. This goes through with our analytical solution. And so in the homework, you're going to have to not only derive the analytical solution, but also just do these plots as well. But you can see that, if our probability of the two populations are off, it does change where the line is, because if we don't have an equal probability of being in either plot, then, it's maybe more likely that, an animal of 1.95 meters like before is a wolf now, if the wolves are more likely. And so this is just giving you an example about how to plot it, how to use Python to just generate examples for the homework, but also just visualize the problems that you're working on. In the next homework assignment, in the next lecture, we're going to be talking about hidden Markov models and Bayesian networks. We're going to be doing a simple example with rainy and sunny days and doing an inference on the probability of a certain occurrence happening. Thanks so much, and we'll talk again next week.